Hello, my name is Michael Glinsky. I'm going to be talking to you about line VISAR measurements of the energy deposition for the next generation MagLIF laser preheat that had been conducted at NIF. Here are my other co-authors who have contributed to this work. MagLIF is a magnetic direct drive ICF platform that requires coupling of 20 to 30 kilojoules of laser energy into a gas pipe target. As was discussed earlier in detail by Brad Pollock in this session, NIF is the only facility that can drive full-scale targets at the design energy. The intended magnetic gas fill pressures are 5 milligrams per cc of D2, and that the NIF experiments use neopentane fills to achieve similar electron densities without the need for cryo, which allows for both thin windows and for magnetic fields at the same time. That quickly, MagLIF is a magnetic direct drive ICF platform where the plasma is initially magnetized by azimuthal field coils to give about a 10 to 20 Tesla as axial field, which will be up to 30 to 40 Tesla in the next generation. A preheat laser then comes in to heat the plasma and put it on a higher adiabat. So when it is compressed by the large axial Z current, which creates a azimuthal field which compresses the plasma, that it will get to thermonuclear conditions that will burn. The geometry of the VISAR measurement is shown here, where the laser comes in through, the VISAR laser comes in through this protective cone to do the VISAR measurement on an area of the target that is flattened and coated with aluminum. Here is a picture of the actual target, and here is the 1D simulation geometry showing the hydrocarbon-gas, the laser being deposited into the center of that, a plastic wall with an aluminum flyer on the outside. It will be shown that VISAR is a direct measurement of the energy deposited, and this work develops the data analysis framework to estimate the deposit energy with uncertainty. An ensemble of 500 1D hydrosimulations were done. Here are the base case parameters with 4 independent parameters associated with the laser deposition, and then 3 dependent parameters that are then able to be measured from this. This goes and shows the base case evolution as a function of the independent parameter R. Shown are the electron density, temperature, and radial velocity. I call your attention to the flyer plate here, which has an ablation off of the inner surface driven by the laser shine onto that surface. You will go and watch this small little shock go through the flyer plate from the ablation, and then a main shock from the laser deposition approach and go through that flyer plate. Here you can see the small shock going through the flyer plate, the main shock approaching the flyer plate, the ablation of the inner surface. You now see the main shock entering the flyer plate, transient the flyer plate, and now emerging on the outside of the flyer plate. Here are time-dependent quantities, different energies. You can see the energy of the laser being deposited, and then the transfer of that energy into the flyer plate. This measures what the VISAR measures, which is the velocity on the outside of the flyer plate. And it's easier to go and see the arrival time of the initial ablation shock and the main shock by taking the derivative of this measurement. This goes and shows the evolution of the outside velocity of the flyer plate given different initial conditions that were sampled. Notice also the evolution at the later times is being caused by a shock that's bouncing back in the outer spalled layer. This is a closer look at the flyer plate showing these outer spalled layers, which go and range from 15 in this case to 2 to 4 to none in this case. You also can see the ablation of the inner surface. Here are the temporal evolution of these different profiles. You can see the shock of the ablation transiting through the flyer layer. Soon you'll be able to see the arrival of the main shock here. Now here comes the arrival of the main shock for this case in transient through the flyer plate. Here comes the main shock in this case transiting through the flyer plate. Now as time goes on, you can start seeing the spallation of the outside layers and the development of those differing number of layers depending upon the material strength and failure properties and the laser power. When we go and plot two dependent properties, being the arrival time and the deposited laser energy, we found a very good log-log correlation with the fractional error in that correlation of the energy being equal to the fractional error in the time. When we go and add the uncertainty and the arrival of the energy at that axial position, that the uncertainty increases from 1 nanosecond up to 2 nanoseconds. This can be removed by using the fact that this first ablation shock does not spall the outside layer, so there is a good relationship between the size of that shock and the arrival time. So you can use the size of the shock to correct the arrival time of that shock to the correct position, which then removes the uncertainty in the arrival time. That what is done in practice is that the shock arrival is measured as a function of axial position from the VISAR measurement that is seen here. It is then corrected by the arrival of that shock from at that axial position from an independent measurement. Then the relationship is then used that was derived a couple view graphs ago to be able to go and transform the VISAR measurement into deposited energy per unit length as a function of axial position with uncertainty that can be compared to numerical simulation values. The energy is estimated to about 10%, and that the pre-shock from the ablation inner wall surface can be used as a time fiducial to reduce the time origin uncertainty. The forward path includes going and putting a window on the outside of the flyer plate to stop the spallation, to allow us to use the delta velocity as a direct measurement of the deposited energy. Also to add high strain rate material models for the aluminum. Increase the radius to decrease the fractional error in the estimated energy deposited. Model other cases that we are measuring, as well as using a more complete Bayesian analysis using all of the data in order to be able to get a reduction in the uncertainty in the estimated energy deposited. Thank you very much.